All right, very quickly, I'd like to introduce myself. So my name is Nicolas Labonte. I'm a security and compliance analyst here at eConcordia. I'm interested in tech, arts, and making cool things. I've taken up 3D printing in mid 2020 and have been in love with it ever since, though it has gotten me frustrated on more than a few occasions. So my information, LinkedIn, and email are right here if you'd like to get in contact at a later point. So I thought it would be interesting to start with a few instances of 3D printing in the news. Well, not only will it give you a small peek into the possibilities it brings to the table, but also it's fun to work backwards from there and see how it all works. So we have here an example of 3D printing in small number but large size, where a designer made a very cool chair out of recycled PETG. PETG is a slight variation of the PET material that's very commonly used for single-use water bottles. So all in all, this person-sized chair took about 12 hours to print, which is really not bad for such a big item. Here, Adidas now sells running shoes with 3D printed midsoles that push your feet forward. The midsole is this whitish part right here. So this is 3D printed. Why? Well, because it uses unique geometries made possible by 3D printing. It stores momentum and releases it, thus pushing the foot forward for a gentle boost. The last news will be kept as a surprise for the end because it will tie in nicely with our last subject. All right, so let's get started. So we talked about 3D printing, but what is it really? Well, in essence, 3D printing is a type of additive manufacturing. So let's say you were to start with a piece of wood and turn it into a spoon. You would remove material until you get the shape that you want. That's called subtractive manufacturing, as you remove material to create something. 3D printing being an additive manufacturing process, you would add material onto itself to create the desired shape. The most common additive manufacturing method is called injection molding. It's a process where molten plastic is poured into a metal mold to create shapes. And that is how most plastic products are made today. And it's very interesting, although it sadly won't be the subject of today's presentation. Now, there are some real benefits to additive manufacturing. Since you're adding material, you're only using the amount that you need instead of removing from an expensive block or chunk of material. Also, some types of geometry would simply be impossible, or at least very impractical, sorry, to achieve using additive manufacturing or even injection molding. A good example of that is the Adidas shoes. Um, Doing this in a mold would be next to impossible because you would have to, when you would remove the mold, you couldn't have that geometry inside because it's intertwining. So that's a type of geometry that is almost solely practical when 3D printing. Now let's get into the basic principles of 3D printing. So 3D printing is actually a fairly broad term because it encompasses several types of technologies and materials. For hobbyists, the two most common types are FDM for fused deposition modeling or SLA for stereolithography. So SLA uses UV light to cure a resin-like substance, and it can achieve perfect quality for small objects, such as figurines and miniatures, but it just can't quite match the size and strength of FDM parts. FDM is the most common technology and, in my opinion, the most useful. And so this is what we'll be focusing on today. We'll be talking about FDM printing. So to make an object using an FDM machine, you need, in essence, three things. You need a digital file of the item that you're trying to create, which will let the machine know what to do and when. You need material or materials to add to one another to create a shape. And of course, you will need a machine that's capable of melting and depositing material on a platform, usually using a Cartesian coordinate system. So what's interesting is that 3D printing is actually very straightforward. Now, I know that you may find all the subtleties overwhelming at first, but the core principle is very simple. It's stacking material onto itself in layers until a shape is produced, the way you would make soft serve ice cream or swirls of frosting on a cupcake. It's so self-evident, in fact, that it's been thought about for decades before it became an actual technological possibility. So in his short story, Things Pass By, author Murray Leinster describes a machine as follows, and I quote, "But this constructor is both efficient and flexible. I feed magnetronic plastics, the stuff they make houses and ships of nowadays, into this moving arm. It makes drawings in the air. Following drawings, it scans with photocells. But plastics come out of the end of the drawing arm and harden as it comes. Following drawings only." Does that sound familiar to you? And it's crazy to realize that this was written in the 50s, so way before any practical use of 3D printing. In a more contemporary example, fellow science fiction nerds may recall Star Trek's Replicator from the 70s. Fun fact, the one of the first popular consumer 3D printer was called the MakerBot Replicator. Coincidence? I'll let you decide. So I'll go through the process very simply, and then we'll move on to a bit more advanced step as we go. So we'll talk about depositing material into shapes later, but for now, we need to get some plastics melted. So most hobbyist level printers will use spools of material, which is filament rolled like a meter long strand or what meters long strand, like one big spaghetti rolled onto a spool. So this filament will then be pushed or pulled through an extruder with tooth-like gears and using a small electric motor all the way to a hot end. A hot end is a component which is made up of several other components. So first, the filament will travel through the heat break, which is kept relatively cool, usually using a small fan, just to ensure that the material doesn't soften too soon and create a clog. From there, it continues its journey into the heat block, where it is heated by a thermistor and a heater cartridge. So the heater cartridge will create heat, which will spread through the heatsink, or sorry, the heat block, and then a thermistor will make sure that the temperature is the right temperature. So it will adjust the power of the heater cartridge to adapt to the temperature. And it all ends at the nozzle, where the filament is pushed through a smaller hole and then exits onto the printing platform. I'll mention this just a bit later on, but usually most consumer level filaments are 1.75 millimeters in diameter, and most nozzle orifices are 0.4 millimeter. Again, it does depend, but On average, it is zero point 0.4. So it does create quite a bit of pressure because the filament is pushed through a much smaller orifice to make sure that the coverage is good enough. So now, of course, we have to make that nozzle move. Otherwise, all we get is a big blob. So most consumer level 3D printer will use one of two movement types. We have the bed slinger types or the Core XY concept for movement. This isn't the most important part, but it's an interesting fact that I'd like to share with you. So on all 3D printers, FDM printers that is, we have a tool head. In that tool head is the uh, my apologies, the hot end that we talked about just a few slides ago. So this one has fans on it for cooling the parts, but underneath that cap, that shroud, is the hot end. So the hot end has to move um, uh, uh, back and forth to actually create the lines for the printer to be created layer by layer. So one of the two movement types, Core XY, the bed moves on the Z axis, and then the tool head moves on the X and Y, as shown right here on the left-hand side. Um, on the other hand, we have the very popular bed slinger type. So here, the bed will only move in the Y direction, so forwards and backwards, and then the tool head will move up, down, and left and right. Again, it all amounts to the same. It's just the two ways that that movement is created in Bedslinger. There is similarities in both. They both use belts, pulleys, and motors to move the tool head. This one here, the Bedslinger, again, it takes its nickname from the fact that the tool head moves on the X and Z axis, and the bed will move on the y-axis, thus flinging the bed forwards and backwards, if you like, and that's where the nickname is from. The last but very important element is the ability to stack layers one onto the other on the bed. That's how things are printed. They're printed layer by layer, and then those layers are fused by heat, and it makes an object. So of course, to do this, the printer will work in layers, each with a predetermined thickness. This is referred to as the layer height. We have a few examples here on the right-hand side. Layer height affects quite a few things in the model, such as general print quality and print time. Usually, a layer height of 0.2 millimeter is used. So that would mean that every layer making up the object would be 0.2 millimeter or 2 microns. Sorry, 200 microns. So it's, 200 microns, but 0.2 millimeter. So once the print is completed, the object can simply be removed from the printing platform. And you decide how you want to remove this. You can use a bit of force. Usually you have a metal spatula or scraper that's provided with the printer, or some printers can also have a flexible bed to pop the print off. And all of this, the movements and the extrusions are all controlled by macro controllers and motors using commands known as G code. So believe it or not, now that we know about movement and getting plastics melted, we have the basis for most 3D printers out there, and the rest is just variables. It's size, speed, materials, and etc. But before we move further, I'd like to just take a few moments to illustrate some of the elements that make 3D printing particularly easy and efficient for many types of projects. The example that we have here is supports. So 3D printing software, which we'll cover in just a moment, can create a support structure to support the deposited material where it would otherwise droop from the heat or simply print in midair. As you see right here, this portion lays flat on the bed, so it's easy to print. But then as you get here, this part would simply print in midair, which is not yet possible. So what we have here is a automatically generated support structure, and this can simply be pulled away from the model. It is done in a way that it doesn't fuse as well to the actual model, so it can simply be pulled away, leaving the model fresh and complete with this perfect overhang. We have flexible filaments. So many printers have the ability to print flexible materials such as TPU, which we'll cover in just a bit. And those are very resilient and can be used for anything from dampeners to dog toys, and also very commonly for phone cases as well. Next up, we have multicolor and multi-material. So some printers have the ability to use more than one color or type of filament on a single print, which makes it, of course, very easy to create professional-looking toys or other objects benefiting from a dash of creativity. Next, as we'll see later, there is size. So you see here we have one of these smaller printers, a Prusa Mini, which is about as small as a couple of shoeboxes. And then we have ones that are human-sized or even sometimes building-sized, as we'll see at the end of our session. So now, if you're as curious as me, you're probably starting to wonder how you can use 3D printer in your very own creative endeavors. It's good timing because in the next few chapters, I'll be going over everything you need to know and have in order to get from project to printed. Of course, for the sake of time, I will forgo some of the most obscure tips and tricks, but remember that you have my contact information, and I'm always more than happy to help a fellow creative. Let's start with getting a printer. So in essence, the printer you will have, you will need to fit your needs for sure. So for most beginners, a simple bed slinger type will be more than enough. But in some cases, you may have specific requirements, such as a slightly bigger bed size, or an enclosure to print draft sensitive, let's say, materials. Some printers also can print specialty materials, such as carbon fiber reinforced or even glow in the dark plastics. And some even have the ability to print in multiple colors at once, or even with two print heads at the same time. Here we have a couple of examples. These are all Bamboo Lab machines, and we have here two instances of their AMS or automatic material system. So, of course, whether you're looking to make money out of that hobby or simply create things for yourself and your close ones, budget will always be a decisive factor. But luckily, printers run the gamut in terms of price, so there's something for everyone. Here are some of the most popular models, illustrating the wide array of machines available on the market today. So you can see you can get a very reliable printer starting from a few $100, and you can go all the way up the chain depending on your needs, your budgets, and of course, what you'd like to spend money on. Now, what's interesting is that if you're the tinkering type like I am, you don't even have to restrict yourself to buying a pre-assembled printer. In fact, 3D printers started as DIY projects, and this tradition is well and alive to this day. There are even very well documented and open source projects with thriving communities and people really eager to help. Well, coupled with the fact that you have total control over the parts and capabilities of the printer that you build, and that is a very exciting adventure. it's no wonder that many turn to this option. An example of popular community-driven projects include these right here, the Voron, Rack Rigs, and VZBots. I have a VZBot myself that I built, and I also have a few other printers that are bought out of the box, but that you can modify to add cameras, better hot ends, better fans, or just for cosmetics. So now we have a printer, but we are still missing a vital component, which is the material or filament. So consumer grade FDM 3D printers use spools of microplastics available in wide array of types and colors. The very first thing to consider is the requirements of your printed part. So rigidity, heat resistance, water resistance, fit and finish, etc. So let's go over some of the most popular options and some that are a bit newer on the market. First up, we have PLA or polylactic acid. PLA is the bread and butter of hobbyists. It is cheap at around $30 per kilo, and that is printed. So an object weighing a kilo would take a kilo of material because it is an additive manufacturing process. And so it is cheap and it produces high quality parts with some of the lowest hardware requirements of all. You can print PLA on anything. It's very easy to print with and offers high rigidity. It doesn't flex at all. However, it does begin to soften at around 60 degrees Celsius and it's a little brittle. But it's a perfect material for almost anything that doesn't require very high strength or temperature resistance. What's more, most PLA is made from renewable sources such as corn bark or sugarcane. Next up, we have ETG or polyethylene terephthalate glycol. So that's a twist on the very ubiquitous PET, of which most plastic bottles and containers are made of. So glycol, G, it has been added to enhance its characteristics and make it more suitable for 3D printing, as PET is used usually for injection molding. So PTG has some flexibility, which makes it very useful for things like spring mechanisms or parts that will be subject to frequent oscillation. It also stays solid up to around 85 degrees, which makes it suitable for exterior or sun use. So this one you are almost certainly familiar with in some aspect. So ABS or acrylonitrile butadiene styrene, it is extremely common in injection molded items. In fact, most plastic items today are made out of ABS because it is a very resilient material and supports temperatures of up to around 105 Celsius, making it both dishwasher safe and even food safe in some instances. However, it can be a bit trickier to print as the item may contract and warp during printing if it is subject to drafts. So for such materials, an enclosed 3D printer is recommended. Also, one should ensure proper ventilation of their workspace when printing ABS because its fume does contain VOCs, which are microparticles that are damaging to the health. It also tends to stink up the room. In 3D printing, ABS is slowly falling out of favor, and ASA, a very similar microplastics, is considered preferable. TPU, by far one of the most fun and useful microplastic for 3D printing, by far my favorite. So TPU or thermoplastic polyurethane is a flexible filament that's also incredibly resilient. It's used in phone cases, shoes, and as a modern replacement for rubber. TPU comes in a few types, mostly affecting its amount of flex or crush resistance, categorized by what we called shore hardness. It is this chart right here. So the shore hardness scale is composed of both a letter and a number. So the bigger the number, the harder the material. Um, so it's available in a wide array of applications and types. Usually for FDM 3D printing, we will tend to be in the A82 to A95 range. So you see just around the hardness of a tire thread or a shoe heel, although it goes all the way to hard hats and all the way down to the consistency of jelly candy. In fact, one of the factors that affects TPU squishiness, if you like, the most is its internal structure. In the slicer software that we will see in just a few minutes, you have the possibility to choose how many layers compose the walls, top layers, bottom layers, and also the infill. So infill is, let's say a part is by default empty, there's void. Adding infill will fill that void by a percentage and using a certain type. So let's say I have a 10% infill. 10% of the void, the empty space, will be filled with plastics in a pattern that I will have chosen, either triangle, rectangular, or my favorite gyroid. So what makes TPU super interesting in that sense is that playing around with um, even only infill will make a drastically different part. There are also variation on these filaments, such as the inclusion of chopped carbon fibers, right here. These help greatly increase rigidity throughout the part. Usually they're demarcated with CF as either a prefix or a suffix. For example, you have CFPLA, CFPTG, or CF nylon. You also have filaments with added particles. It's also commonly available, such as PLA with wood or metal components. What's interesting is that these give the items some of their characteristics, such as conductivity or a wood-like feel, fit, and finish. For example, I have a wood filament from a company called Hatchbox that I like quite a bit. So it is PLA filled with 30% wood granules or powder. And once printed, it does look just like wood. And in fact, I can stain it just like wood. So it makes for very interesting and nice looking parts for very cheap. Lastly, PLA has its very own variation called Silk PLA, or gradients also are available. So these are usually a bit weaker than PLA, but they give it a really nice premium shine and silky finish. So we mentioned earlier that we needed a machine, filament, and a digital file. But what exactly would that digital file be? Well, it will usually take two forms. So the first is a digital 3D model in formats like .stl, .3mf, .obj, and others. So these are created using CAD or computer-aided design software like SketchUp, 3ds Max, Fusion 360, Blender, and others. Some of these may sound familiar to you. They are software for designing 3D geometry on a computer. So, of course, you can create your own 3D models, but if you feel comfortable and you have a specific need, uh, many of us just don't have the time, resources, or knowledge to make our own designs. But luckily, there is often no need to. So there are many repositories of free, high quality models available for download online. Personally, I don't recall once wanting to print something and not being able to find a suitable alternative online, be it a tool, a gadget, a gift, uh, anything, trinkets. Honestly, it's never happened to me. In fact, in most cases, I found designs that were way better and more creative than the ones I would have thought of. The most popular free model repositories are Thingiverse, Printables, and Thangs. Thanks is also actually an aggregator, so it will look up several websites for you and present them to you on one page. Although it is a bit less fun to use than my personal favorite, which is Printable and Thingiverse. So once we have our file, our 3D computer file ready, there's one more step we need to take to make it printable, and that is putting it through a slicer software. So in essence, a digital 3D file is made up of polygons, and it is very suitable for displaying in a computer application. However, due to the processes involved in 3D printing, chief among which the fact that we print in layers, we can't simply send the file to the printer. It wouldn't know what to do with it. That's where the slicer software comes in handy. It slices the model into horizontal slices from bottom to top and creates the proper commands that can be interpreted by the printer software and controller. So here we have an example of a few commands. These are known as G-code commands. So once sliced, your file would be a bunch of these, which would tell the printer heat up to this temperature, move to this position, extrude material by this quantity at this speed. And once you have thousands of these lines, you have a file that can tell a printer what to do and when to get you your coveted 3D printed file. Um, and it's also in the slicer that you would specify your desired settings, like I said, for example, infill, but also such as speed, layer height, temperatures, fan speed, strength, and other quality parameters. In most cases, off-the-shelf printers, they come with pre-configured profiles, so you can simply select the material and quantity and let the software do the rest. Once we have our G-code file, we can finally start the print. I'd like to take just a moment now that we're nearing the end of the technical portion of this presentation to take a bit of a step back. Here I am attempting to be thorough and to go through all the reasons why and how 3D printing works. However, I know that this can be very overwhelming when taken in all at once. I would like to counteract this with my personal opinion. 3D printing is fun. It's rewarding, and it has never been easier. It does require a desire to learn and to stick through the process the first few times, but the 3D printing community is among the most friendly and generous ones out there on the internet. It's also important to know that most pre-built printers will come with everything you need to get started, including filament samples, tools, documentation, spare parts, slicers, settings, and files already prepared and ready for printing, usually stored on a USB drive that comes with the printer. All in all, most printers will have you printing in 30 minutes or less. So please don't let my deep dive discourage you. In fact, I really do recommend it as a hobby and a tool. So lastly, the moment we've all been waiting for, the printing. We have to get our G-code onto our printer's storage. And that can be done in many ways, depending on the features offered by the printer. Some have USB ports, some have SD or micro SD slots, some even have Wi-Fi and full web applications. Either way, once the file is in the right place, you simply press print. The printer will go through its pre-programmed routine, which includes touching sensors on all axes to know its print area and where the tool head is. That's a process known as homing. Then it will preheat its nozzle and bed. Some printers may require a few more steps, either automated or manual, such as heating up a chamber or using a probe to level the bed. Once all those steps are taken care of, the nozzle goes to its start position and starts printing the shape layer by layer by layer. When required, fans will cool down the freshly laid filament to ensure a good mix of material bonding and surface quality. When the print is finished, as I mentioned, you can take the part of the bed by simply using a bit of force, the provided metal scraper, or flexing the bed in case your printer supports that feature. So, in my opinion, 3D printing is nothing short of a revolution and will play an important role in many spheres of society over the next decades. I'd like to go just over a few reasons why I think so. The most obvious, although not the most important, reason is that 3D printing puts affordable, scalable, and versatile means of production into the hands of consumers, lessening the reliance on mass produced goods. This in turn creates new opportunities for local markets and small businesses, as well as having a potentially important impact on shipping and pollution related challenges. Home hobbyists now have the possibility of exploring new creative outlets. What's more, the ever growing community of bright enthusiasts have already contributed to numerous new discoveries and improvements, not only in 3D printing, but in other fields as well, most of which are now available as open source projects for all to use. The issue of right to repair, the principle that consumers should have the possibility of servicing items they own, is very near and dear to my heart. Goods, especially electronics, have gotten so complex, and inversely, their lifespans have been drastically reduced since the mid 20th century. Who hasn't had to take their car to the garage because a plastic piece broke or had their dishwasher leak because of a poor quality fitting? The sad truth is that whether through planned obsolescence or a simple lack of focus on long term quality, modern goods end up in landfills faster and faster. And that's an issue we simply can no longer afford to ignore. So in comes 3D printing and the growing repositories of 3D models available online. I have stopped counting the number of household items I was able to repair, restore, or improve using 3D printing. Various mounts and stands, clips to hang Christmas lights, wall supports for vacuuming or cleaning equipment, boating and car parts. All in all, I have saved hundreds of dollars by repairing items I already owned. And that's not counting the custom parts I was able to design, thus avoiding buying things online and contributing to logistic and pollution issues. What's more, new clubs and venues have also appeared around this subject, such as so called repair cafes, where patrons can grab a hot drink and learn how to repair their goods in groups. 3D printing trailblazers like Cruiser Research are even partnering with corporations to create and distribute free 3D model files for repair or improvements of their products, as is the case with the innovative right to repair advocate computer manufacturer Framework, who are in the news recently for making laptops that are simply repairable and upgradable as a user. So the explosive growth of 3D printing has really put pressure on companies to embrace the right to repair movement, and many have since started offering 3D printable models for servicing and repairs. There are times, however, when plastic items have served their purpose and are no longer required, as it is the case with single-use plastic bottles. Luckily, 3D printing has and is having a tangible positive impact here as well. So, new machinery coupled with influencers raising awareness have enabled companies and even home users to recycle many types of microplastics and to turn them back into spools of partially or fully recycled filament for reuse. Many business ventures have grown around this very concept, with one notable example being the YouTube channel Brothers Make, who create unique utility and art items from fully repurposed microplastics. Needless to say, we expect and hope this trend will grow exponentially over the next decades as 3D printing equipment and knowledge becomes more ubiquitous. The future of 3D printing seems very bright indeed. In addition to the economic and ecological benefits we just talked about, I'm really excited about a few trends in particular. So, of course, as with any technology, growing consumer adoption will lead to cheaper, more performant products. And that's exactly what we've been seeing in the last half decade or so. In fact, the last couple of years have been so simply incredible for the 3D printing market with leaps and bounds in terms of features and ease of use, as well as the birth of many new key players, fostering competition for the consumer market. It's hard to tell what's in store for the technology, but I, for one, am very hopeful and excited about what's to come. Here we have an example with a few very technical terms, but this is basically the same printer, 3 years apart, same price, totally different set of feature, taking it from barely printable to absolutely set and forget. So, of course, it wouldn't be a Concordia presentation without at least some mention of academia. A joke aside, though, 3D printing offers incredible new ways to interact with and explain academic subjects, be it in classrooms or in more theoretical contexts. With all the free models already available online, educators have opportunities to create rich and engaging learning experiences. In turn, this can dramatically lessen the financial burden on already underfunded schools, as well as provide teachers with the ability to show their creativity through the usage of 3D printed models, tools, and even scholastic supplies. I have an example here of a few items that are available for absolutely free as downloads on the repository called Thingiverse. These are just some examples related somewhat to academia. So here we have a frog dissection kit, so all 3D printed. Here we have a very cheap drafting set, again 3D printed. These can be quite expensive when made of metal. Here we have a model of a multi-cell, and then we have here a bigger model, so printed in a few parts, but still on a very, very cheap, actually the $280 printer that I mentioned just last line. So here we have the human torso anatomy. Of course, you pay for the filament, but that is it. And those are extremely expensive objects to get your hands on in the professional departments. So another domain that's had 3D printing in their crosshair is the medical organizations and startups using 3D printing principles with specialized materials. Professionals are now able to create dentures, prosthetics, cartilage, and some are even experimenting with 3D printed organs for transplants. This would have, of course, tremendous effects on the healthcare market as it would decrease pricing, decrease wait times, and reliance on animal testing, as well as offer the ability to customize the organ for a specific recipient, thus reducing the chances of rejection by the body. Other breakthroughs regarding materials have made it possible to 3D print anything from edible chocolate, yes, to houses. Indeed, a few startups have made it easy to print chocolate items for cheap. That is, and it prints just the same way as you print any other 3D model. I'll just take a second to just look at that image. So this is real 3D printed edible chocolate. And I don't know if you can imagine trying to mold that using classic technologies and procedures, but you cannot mold this using injection molding. It's simply a geometry that is enabled by 3D printing alone. On the more practical, though less delicious side, 3D printed housing, usually using a type of concrete, has really started to become more commonplace. This obviously has tremendous implications regarding the costs and timelines related to construction, as well as the environmental impact of using less wood. It's also very heartening to hear that many such projects have been aimed at offering housing to those less fortunate or at risk of homelessness for a very reasonable price. So, congratulations for making it all this way. While 3D printing may not be in your immediate future, I do hope you've understood the fundamentals of the process. If anything, I hope to have conveyed why this technology is becoming more and more popular and why it's something we should really be excited about. The remainder of the time will be dedicated to questions or comments. And in any case, I thank you all very much for your attendance.
Thank you so much, Nicolas, for the very thorough and very detailed presentation. I actually just wanted to pick your brain for one question. Maybe it's not like, maybe the answer doesn't exist yet, but I just wanted to have your opinion because very often people talk about SLA being able to print models that are more detailed, that it seems more seamless, the surface, etc. Do you have any thoughts on whether or not one day or in the short-term future FDM printers can get closer and closer to that quality, or do you feel that the technologies are so different that fundamentally you'll never be able to get the same
That's
thing?
that's an excellent question. In a sense, it comes down to two things. Indeed, SLA printers are fantastic when it comes to detail. It's using an LCD to cure resin. These LCDs can go to 8K on a screen this tiny, so the resolution is intense. It comes down to two things. First of all, the outside finish of resin, once cured and clean, is a bit more. It is more seamless, like you said. It is really a type of finish that is different, and that does play on the eye. And there also is the fact that SLA layer heights are tiny, absolutely tiny, while FDM still at anywhere from 0.08 to 0.04 millimeters. It's still much bigger. There is, however, a few tips and tricks to basically make FDM prints look like SLA prints. Since they are microplastics, most of them are not 100% resistant against chemicals. So, for example, you can treat ABS with acetone or PLA with what's the one where it's always in movies you see someone has a cloth over their mouth and there's a chemical and it
The
makes them
chlor
sleep?
chlor chloro
Yeah,
chlor
chloroform.
chloroform, yeah.
So thank you very much. So acetone for ABS or chloroform for PLA. This will actually melt, very slightly melt the exterior surface, will give it that glow, and will basically erase all traces of layer lines. So back to back, except for the fact that you could do much smaller objects on an SLA, they would look almost identical.
Mm. All right, thank you. Didn't know that.
Yep, you're welcome. No worries. All right. If there's no other questions, I'll let you all have a great evening. Oh, of
Oh,
course. Please.
Hi, can you hear me?
Yes, I can hear you.
Okay, perfect. Yes, your presentation was quite technical, but I tried to follow along. But my question was, I was really interested when you brought up the different materials that the different things that 3D can print, and then you said edible chocolate. And so my next question was, can it be used in fashion?
Absolutely. I did have to choose between several news articles to show, but I've actually seen an article while browsing where jewelry was made using again multiple colors and recycled materials, and it's selling like hotcakes because it is self-sourced. It is on a small scale. It is from recycled materials, and it offers types of geometry that is impractical or again impossible with standard other processes. So it is actually gaining momentum in terms of the fashion market. Yes.
Okay, thank you. That was all.
Thank you.